This tutorial will show how the end length offset and panel zone options in SAP 2000 can be used to model the flexibility that occurs at beam column joints. The flexibility at the joint where a beam connects to a column can significantly impact the overall behavior of a frame structure, so correctly modeling it is important. SAP 2000 offers the ability to easily fine-tune the flexibility at these joints using end-length offsets, which are assigned to frame objects, and panel zones, which are assigned to the joints themselves. We will show both options for a simple steel frame, and we will use lateral displacements to compare behavior, although other quantities, such as member forces and modes, would also be affected. Our model is a simple 3-story, 3-bay frame with W21 beams and W14 columns. It is loaded with a static lateral load called EQ. This is the beam column joint, which is typically referred to as the panel zone when working with steel frames. It is the flexibility within this zone that we wish to model. We will model the flexibility of the beam column joint using 3 different approaches. First, center to center. Historically, this is the most common and is the simplest modeling approach. The beam section is continued to the column center. Second, we will use a rigid end offset, where a rigid link connects the end of the beam at the column face to the column center line. And third, we explicitly model the panel zone with springs. Our first model will use centerline to centerline construction. The length of each element is from joint to joint. This setting is done via the frame object assignments. We select all of the model and go to the Assign Frame End Length Offsets command. Select the Automatic from Connectivity option, and this means that the program will determine the length of the end offset from the actual beam and column sizes. We could also explicitly define the dimensions at each end of the selected object if so desired. Next, we define the rigid zone factor. 0 means no rigid zone, which is centerline to centerline. This means the element runs the full length from joint to joint. One means fully rigid. This means the element is shorter and that a rigid link connects the element to the joint. We can also specify any number between 0 and 1. We are doing a steel frame, but if doing a concrete frame, we might specify 0.5, which means that half of the joint length would be rigid. We will set this to 0, as we are creating a centerline to centerline model first. If we right-click on a column frame object, note that the program has determined the offset based on the beam dimensions. Also note that the rigid zone factor is set to 0. We are now ready to run the analysis. We will switch the elevation view to show the deformed shape due to the static lateral load EQ. Moving the cursor to the top right corner shows a lateral displacement in the local U1 direction of 0.483 inches. Remember this number for future comparison to the other beam column joint models we will run. Now we will do an analysis using rigid links in the beam column joint. We unlock the model to remove the results of the centerline to centerline analysis and select the entire model again. Once more, we go to the Assign, Frame, End Offsets command. But this time, we will set the rigid zone factor equal to 1. This is completely rigid. If we right-click on a beam frame object, note that the program has determined the beam offset links based on the column dimensions. Also note that the rigid zone factor is set to 1. We will now rerun the analysis. Now when we hold the cursor on the top corner, we see that the lateral displacement has decreased to 0.399 inches, less than the previous centerline analysis of 0.483 inches. This makes sense since the model is now less flexible. The next approach we will show is where the beam column joint is explicitly modeled using the panel zone option. What we are looking to do is include the effects of panel zone deformations. That is, how the zone located at the intersection of a column and beam deforms. Panel zone behavior is modeled with springs that connect beams to column joints. In SAP2000, these springs are rotational springs, based on the so-called scissor model that approximate the shear deformation of the panel zone. Check to make sure that the rigid zone factor is still set to 1. We will leave these set to 1 so that all of the joint flexibility will be controlled by the panel zone springs. Once again, unlock the model to remove the results of the previous analysis. Unlike the end length offsets that were assigned to the frames, panel zones are assigned to the joints. Select all of the joints above the base that have beams framing into them, and this time go to the Assign Joint Panel Zones command. Again, the panel zone option creates rotational springs that connect the beam to the column. Springs can be based on the column properties plus doubler plates, user-specified spring stiffnesses, or previously defined link objects may be used. Here we will use the elastic properties from column option, and note that this option can only be used with the beams to other objects option. A right-click on a joint shows that the spring property is from the column property. Note that no doubler plate thickness is used. We will now rerun the analysis. The lateral displacement at the corner is now 0.531 inches. As expected, the displacement when including the panel zone deformation is greater than that when using just the rigid zone factor of 1 without the panel zone springs. For our last model, we are going to add a doubler plate to see how the displacement is affected. Again, we unlock the model to delete the previous results and select all of the joints above the base. this time when we go to the Assign, Joints, Panel Zones command. We will select the Elastic Properties from Column and Doubler Plate option, and we'll add a 1/2 inch thick plate. A right-click on a joint shows that the spring property is again from the column property, but that this time a 1/2 inch doubler plate has been added. Running the analysis once more, and then holding the cursor on the top corner, we see that the lateral displacement has decreased to 0.476 inches, less than that for the model where the panel zones were without doubler plates. A final tally of our displacements for the model using the 4 different beam column joint flexibility settings is as follows. The analysis where the beam column joint was modeled as completely rigid resulted in the smallest displacement, as expected, and the analysis where the panel zones were explicitly modeled using panel zone springs based on the column properties resulted in the largest displacements. Thus, in conclusion, it is important to correctly account for beam column joint flexibility in frames, as this behavior can have a significant impact on analysis results. This concludes this tutorial on using end offsets and panel zones in SAP 2000.